Hello to you all, hope you're doing well. Okay, I'm going to talk to you about differentiating the natural log of x. The reason for this is in your CB paper, the FP1 paper I gave you, remember that? Hope you're having fun with that. There's a question there, question 3, that requires you to differentiate a natural logarithm, and you've not actually covered that yet, have you? Well, what I'm going to do is I'm just going to give you the answer first of all, and then show you an explanation, not a proof, of why it is the answer. So if y equals natural log of x, the result that you're looking for is dy dx is 1 over x. Okay. Well, why is that? Well, there are several ways of trying to prove it, actually. You can either prove literally that a derivative of natural log of x is 1 over x by first principles or some other method. Or what you can do is go the other way round. What I mean by that is use integration to do the result. Okay, so that is, if I tell you that the integral of 1 over x with respect to x is natural log of x plus c, of course, then because the integral from left to right of 1 over x is natural log of x, then from right to left, sometimes called the antiderivative or anti-derivative if you're American. But we don't really have a word for it in English. We should do, really, because I think antiderivative is a good word. Okay, but the opposite, the inverse of integration, is differentiating. If we differentiate natural log of x, you get 1 over x. Okay, so what I'm saying to you is, if you accept this integral result here, then working from right to left, you must also accept that differentiating this, you get back to that again. Okay, hence that result there. So why does that work? Because that begs the question now, well, if you're not going to explain to us, why this works, can you at least explain to us why this works? And that's rather difficult to do as well. All right. In fact, when I'm doing this with year 13, I never give the actual proof of it, okay, because it's rather complicated. You just need to know the result. But I can give you a reason, though, which will satisfy you for the moment. Now, I can't remember when it was, but at some point in time, whether it was the 18th century or before, I can't remember. Well, there's Newton was 1642, that's when he was born. And so that was 17th century. So let's give it another 100 years, shall we, for calculus to take off. So let's call it the 18th century. But there was a point in time when mathematicians were interested in a topic called quadrature. What on earth is that? Quadrature. So let's just spell it out for you. So Q-U-A-D, quadrature. Okay. The actual topic is nothing like it sounds it's going to be. Quadrature is about finding the area bounded between the curve y equals 1 over x and the positive x-axis. Okay, investigating the area of the reciprocal function y equals 1 over x and the x-axis. Okay, and in their investigations they came up with a really fascinating result. Okay, really fascinating result. They discovered that the area bounded between these two lines here, the line x equals 1 and the line x equals e, and e was a number that was known at the time. Okay, e was known to be 2.718281828, and then something. It's an irrational number. It's just got this nice little pattern of meaning. E wasn't known at the time. Okay, it was already discovered. Yeah, which is why I'm saying 18th century. At least, okay, if you look it up, then you might find it was different. Do correct me. Okay, I'm just trying to do it from guesswork, basically. I've not looked up when it was. But they came up with this really fascinating discovery. They came up with the area, the area that was shaded in there was, what do you think it's going to be? Well, it was just 1. It's precisely 1, which is really fascinating. The reason it's fascinating is because E itself is an irrational number, of course. And this curve is not exactly the most straightforward shape, is it? It's not like a rectangle triangle, is it? It's pretty easy. No, they came up with the area, this is 1, which is really fascinating. Okay, which led them to a particular conclusion. Okay, the conclusion is this. Now, when you're integrating to find an area, what you do is you write down the integral of the function you're considering, in this case 1 over x dx, and at the top and bottom of the integral sign you write down the limits between which you're integrating, in which case it's 1 and e. And when you write down your answer, you put your answer in these type brackets, sometimes called square brackets, And then what you do is you write down the limits here and here again. And the idea is that you substitute in the limits into your function answer, okay? Your integral of 1 over x, you substitute it in, okay? Now, we know that the answer is going to be 1. This is kind of a working backwards thing. This is like, we know the answer through hindsight kind of thing, okay? They discovered this. Now, the discovery was that for this to work, the answer must be the natural log of x. That's the only way for it to work. And I'll show you why it works. Because when you substitute in each of these limits one at a time, you do the top one first. So you do natural log of e, and then you substitute in the bottom one and take the difference, natural log of 1. Why do you take the difference? Because basically the first one gives you the area from the y-axis up to that point, and then the second one gives you the area from the y-axis up to that point, and then obviously if you just want the shaded area, you do all the way up to there, subtract to there, okay? Yeah, just on a side note, this bit here, of course, the area of that, what's that going to be? That's like a Gabriel's horn type question, isn't it? If as you actually looked at it, because of the infinite continuation of that curve up there. Anyway, this is a finite area. So what is this? Well, the natural log of e is just 1, and the natural log of 1 is just 0. Okay, why is that? Well, I'm running out of space here. Let's just zoom in a bit, shall we? So you know that the log of base a of a is 1. You've done logarithms already. Okay, and when we say the natural log, we are talking about base e here. And we know then that the natural log of e is going to be 1. Log base e of e is 1. And also, the log of any base of 1 is 0. So same again, log base e of 1 is going to be 0. Okay, so when we write out natural log like this, we're saying log base e. So log base e of e is 1, natural log of e is 1, and log base e of 1 is 0, natural log of 1 is 0, hence you get 1. So can you see, because the answer is 1, working backwards, we must have this result here, okay? And that was a rather important discovery in mathematics, because it helped us to see quite clearly this really important result here. All you need to do is remember the result, integral 1 over x is natural log of x. And so, to borrow that well-used term, the antiderivative of natural log of x must be 1 over x. So all of that just to show you this result here, okay, which is what you need to use, okay. Now I've talked about that in great depth. I'm hoping that helps you a little bit. And let's just talk about a couple of examples. It's actually quite difficult for me to operate my camera, phone, and rub the board or write on the board at the same time. So I hope you think I'm doing a good job. Give it a thumbs up if you think I'm doing a good job on that. Okay. Well, look, so if you look at question 3, you asked to differentiate a natural log. Okay. Well, let me give you an example to help you with that. Suppose instead you wanted to differentiate this natural log of, let's just call it x plus 1. Well, what is that? Well, the answer is quite simply, let me just write it down, 1 over x plus 1. How does that work? Okay, well, the simple explanation is when you do the natural logarithm of something, that something in brackets just goes in the denominator like that. Okay, that's the simplest explanation for this type of example. But what if you say, well, look, I'm not happy with that. I'm happy with this, differentiate natural log of x to get that, but I'm not happy with this. Well, let's just try and explain why that is. Let's just instead say, well, I'm not happy with differentiating natural log of x plus 1 because you've changed the brackets now. You've changed it from x to x plus 1. So let's just make a substitution. Let's instead say, well, let's just call this something different so that we're happy, okay? Let's let u be x plus 1 instead and make a quick substitution. So what we're saying is we want to differentiate this natural log of u. And you should say, well, I'm happy with that because I know how to do that. Because of our result you showed me there, if I just swap the letter around, if you have natural log of u instead, it should be the case that dy du is equal to 1 over u. There you are. I'm happy I've differentiated it. Oh, but hang on. This is in terms of u. I need an answer in terms of x. Okay. Well, it's not just simply a case of putting this in there. Okay. It's a case of we need to know what dy dx is. Okay. So yeah, dy du is 1 over x plus 1. But why does it explain what dy dx is? Well, what we need to do is we need to differentiate that as well. So du dx, if you differentiate that, derivative of u with respect to x is 1, because when you differentiate x plus 1, you get 1. And then we're going to use something called the chain rule, which is this. I'll write it down here for you. dy dx is dy du, that's a y by the way, times du dx. Why does that work? Because the du's will cancel if you treat these like fractions. dy dx, you see. dy du times du dx. And so you've got dy du is 1 over u, du dx is 1, 1 over u times 1 is 1 over u, hence dy dx is 1 over x plus 1. Okay, happy with that? I'm so glad you said yes. Let me give you another example, okay, because I did say it's not always as simple as putting the brackets in the denominator. So let me just give you an example like this, okay. What if you had natural log of 7, I love choosing the number 7, mainly because it's a prime number, okay. 2 is a very common number, but after number 2 I normally go for 5 or 7. I usually go for the prime numbers, I like prime numbers. Anyway, so what I'm saying to you is the answer is not as simple as, well, let's just put in the 7x minus 1 on the bottom and then we're done. It's not. So I'm just going to put a not equal to for the moment, okay? It's not the same. To understand why, you've got to use the chain rule that I just showed you. Now I'm just going to put my working down by here for this bit, okay? Well, look, we're going to do the same sort of approach. We're going to say, look, let u be the thing in brackets, 7x minus 1. Because then, you see, we can write y is equal to the natural log of u, can't we? And then we've got a similar sort of situation. Natural log of u, differentiate that, dy du is equal to 1 over u. Okay, great. And then you might say, well, let's just put in that there again. Notice I'm not using plug, okay, because let me just show you. This is kind of my kitchen. See, that's a plug there. I plugged that in this morning to have my tea, okay? Unplug it. This is when you plug something in. There. Okay. What we're doing here is I'm not using an appliance. I'm just substituting. Okay. I'm putting in. Okay, so it's just, yeah. I'm sure you can all work out which student that is aimed at. Happy Sunday. Hope you enjoyed that. Yeah. So it's not just a case of just putting that in because we need to find dy dx. Okay. So this is why we need to use the chain rule, you see. We've got u equals this. We also need to work out du dx. Differentiate that. Now, what do you get when you differentiate that with respect to x? You get 7, don't you? When you differentiate that, you get 7. Let me just write out the chain rule again for you. The chain rule, incidentally, is something that is in year 13 calculus. However, you do need to know it in further maths quite early on. In fact, it's one of the first things that you'll be taught once your year 12 course is finished. It's dy du times du dx. You can change that for any letter you want because you don't always have to use u. You could use t or theta, any other letter you want, okay? And so dy dx is dy du times du dx. So that means you're going to be multiplying that by that, okay? So what does that mean? That means for what we're doing, dy dx is that times that. It's 7 over u. 7 over u. And u is 7x minus 1, so let's just put that in. Okay, you get 7 over 7x minus 1. Look at that, see? So let's just change that. Our actual derivative is 7 over 7x minus 1. Yeah, look at that. Let me give you another. This time I'm going to give it in terms of a generalised case, natural log of ax plus b, where a and b are any numbers. Let's just say they're not 0, just to make it worthwhile question in itself. Can you predict what the answer is going to be? Tell you what, pause the video, have a think about it, and then unpause it, okay? I'm hoping that's long enough for you to reach the pause button. Well, hopefully, on the denominator, you've got ax plus b. That's always a given. So it's always the case that that will go on the denominator, but on the numerator, are you figuring out what it is? It's going to be a. Why is that? Okay. Well, if you just go ahead and change all this working, so instead of 7x minus 1, I'm going to write ax plus b there. And then this will be the same. Y equals natural log of u, because u is that. dy du is 1 over u, yes. Du dx, let's just change that. Instead, you could get a when you differentiate that. So let's just write that as a. And then chain rule again. Dy dx, dy du times du dx. And therefore, this times this is going to be a over u. So that's going to be a over ax plus b. Okay, a generalised result. Or the quick explanation is this: when you differentiate this, you've got ax plus b in the brackets on the denominator, and you differentiate the brackets and put it in the numerator. That's all. Okay. So if we give you another example, the natural log of, I did say I like using number 3, didn't I? 3x plus 8. Let's go for an even number that time. Can you work out, oops, let's just put a y equals in there. Let's just sneak that in. Can you work out the derivative of that is? Okay, pause the video. Unpause, wait for the answer. Oh, you thought I was going to write it in there, didn't you? No, I'll tease you a little bit. Right, let's just go and put it in, and on the denominator, 3x plus 8. On the numerator, differentiate that, you get 3. Okay. So when you remember that result, whoa, there goes my pen. Sorry for that. That's a very poor rectangle, isn't it? When you remember this result here, then it's quite easy just to write down what the answers are. Okay. Well, thank you for watching. I'm just going to zoom out in case you want to see all that. Thank you for watching. I'm hoping that you find that useful. As ever, if you've got any questions, just do let me know. Okay. And I'm hoping that you are enjoying the CB papers, or if you haven't started yet, well, I'm sure you're just giving yourself something to look forward to. Okay. Bye-bye.